Hello everybody, welcome into another lesson. So today we are going to talk about the derivative as a rate of change. So in yesterday's lesson we talked about instantaneous rates of change. Well, another term for the instantaneous rate of change, or the slope of the tangent line at a given point on the curve, is called the derivative. When you hear the term derivative, it may scare you at first, but it's just a fancy term for the slope, or the instantaneous rate of change on a curve at a given point of the function. So you have some function f of x at the point a, f of a being your x value, then f of a, of course, is the value of the function at that x value of a. To find the slope, it's the same thing as the derivative at that particular point. This f tick mark a, that is called f prime of a. That denotes the derivative. Whenever you see f prime of something, that means the derivative. The formula for the derivative is the limit as h approaches 0 of f of a plus h minus f of a over h. So you're going to take the limit as h approaches 0 of that f value of a plus h minus the f of a itself divided by h. That is the formula for the derivative of a function at a given x value. So we'll dive into a few examples of what that's going to look like. Alright, so let's see what we got here. We have f of x equals 3 minus 2x plus 4x squared. So we have f of x equals 3 minus 2x plus 4x squared. They want us to find f prime of 1. We're going to find f prime of 1, meaning we're going to find the derivative or the slope of the curve at the given point where x equals 1. What's going to be helpful, of course, is if you find the y value of 1 of the original function. So if we take f of 1 itself, you're going to get 3 minus 2 plus 4. 3 minus 2 is 1 plus 4 is 5. So this is actually going to be at the point 1, 5, where you're going to find the derivative, or the slope of the tangent line, the instantaneous rate of change for this function. So to find now f prime of 1, you're going to take the limit as h approaches 0 of f of 1 plus h, because 1 is your a, then minus f of 1 being your a all over h. Now we just need to plug all this into the original function. So we're going to take the limit as h approaches 0 of f of 1 plus h. So we have to, wherever we see x, we have to put in 1 plus h. So this would be 3 minus 2 times 1 plus h plus 4 times 1 plus h quantity squared minus f of 1, which we've already determined is 5, all that divided by h. And yes, this looks like a hot mess, and right now we cannot use direct substitution, but you're going to see where we're going with this. So we'll work through everything inside the brackets. We'll do the expanding and distributing. So this will turn into the limit as h approaches 0 of 3 minus 2 minus 2h plus 4 times, let's take that 1 plus h to the second power, that'd be 1 plus 2h plus h squared, all that minus 5 over h. Well, this would then turn into the limit as h approaches 0. If we clean this up a bit, 3 minus 2 is 1, minus 2h plus 4 plus 8h plus 4h squared minus 5 all over h. So this would turn into the limit as h approaches 0. We simplify further, you'll end up getting inside the bracket 1 plus 4 is 5, so you would end up getting 5. Then negative 2h plus 8h, that's plus 6h. Then you just have your plus 4h squared. All that minus 5 all over h. Let's simplify the numerator further. 5 minus 5 is 0, so you'll get the limit as h approaches 0 of 6h plus h squared all over h. Well, now we notice in the numerator we can factor out a common h. This would be the limit as h approaches 0 of h times 6 plus h all over h. And now you can cancel out an h between the numerator and denominator. This becomes the limit as h approaches 0 of 6 plus h. You can do direct substitution in for h, and you'll end up getting 6. So the slope of the tangent line at x equals 1 at the point 1, 5, or the derivative at x equals 1 is 6. That would actually be the derivative, or f prime of 1 equals 6. The derivative, the slope of the tangent line, the instantaneous rate of change at that point. And I got a couple more of these, then we're going to do a couple of applied problems. Alright, we're going to do a rational function this time. So we're going to change the variable to f of t. You can have f of x, f of t, what have you. They're just functions. It doesn't really matter what you call your variable. They're still functions. So f of t equals 2t plus 1 all over t plus 3. They want us to find f prime of 2. So we're going to find f prime of 2, in other words, the derivative at f of 2 when x equals 2. So first thing I'm going to say, again, let's take f of 2 itself. That's going to then be 2 times 2 is 4, so you have 4 plus 1 all over 2 plus 3. That gives you 5 over 5, or 1. So f of 2 equals 1. This would end up being at the point 2, 1. So that's where we want to find the derivative, or the slope of the tangent line, or the instantaneous rate of change at the point 2, 1. Now we can begin to find the derivative at x equals 2, so, or t equals 2 rather. So if we take f prime of 2, that's going to equal the limit as h approaches 0 of f of our a, which is 2, plus h, minus f of a, which is f of 2, all over h. Now, wherever you see that t, you put in the 2 plus h. So this would turn into the limit as h approaches 0 of 2 times 2 plus h plus 1 all over 2 plus h plus 3, all that minus your f of 2, which is 1, all over h. And as we see, we're going to end up with a complex fraction. Well, that's all right. We'll deal with that when the time comes. If we simplify a bit, we'll end up getting the limit as h approaches 0. If we simplify the numerator of the numerator, this would end up being 4 plus 2h plus 1 all over 5 plus h, then minus 1 all over h. Well, of course, we need to make the denominator of the numerator to be a common denominator, so this would turn into the limit as h approaches 0. If we simplify the numerator of the numerator, this would turn into 5 plus 2h all over 5 plus h minus the quantity of 5 plus h all over 5 plus h all over h. Let's simplify further. So this is going to turn into, if we take 5 minus 5 is 0, 2h minus h is just h. This would turn into h over, whoops, I need to write this as the limit as such. The limit as h approaches 0 of h all over 5 plus h all over h. And now, of course, we have a complex fraction. We'll invert and multiply. This would turn into the limit as h approaches 0 of h all over 5 plus h times 1 over h. Well, you have a common h in the numerator and denominator that cancels out. This would just turn into the limit as h approaches 0 of 1 over 5 plus h. Now we can just do direct substitution, put in 0 for h, and you get 1/5. Which means in this case that f prime of 2 is going to equal 1/5. That's the slope there, or the instantaneous rate of change, or the tangent line, the slope of the tangent line, or the derivative at the point t equals 2. Let's do another one with finding the instantaneous rate of change or the derivative at a point, and then we'll do a couple of practical examples. So we're going to do a radical function this time. Yeah, it's going to be real fun. Let's see what we got this time. F of x equals the square root of 3x plus 1. So f of x equals the square root of 3x plus 1. We're going to find f prime of 0. So we need to find f prime of 0. Well, first we need to find f of 0 itself. Well, you put in 0 for x, you would get the square root of 0 plus 1, which is 1. So this is going to be at the point 0, 1 on the curve. Now that we've identified the y-coordinate for x equals 0, let's go ahead and find f prime of 0. So we're going to take the limit, so f prime of 0 is going to equal the limit as h approaches 0 of f of 0 plus h minus f of 0 all over h, which really 0 plus h is just going to be f of h. So this would be the limit as h approaches 0, in this case, of f of h minus f of 0 all over h. So 0 plus h, of course, is just h, so this one's not so bad. You're just going to take f of h minus f of 0 over h. Well, wherever you see x, put in h. So this will turn into the limit as h approaches 0 of the square root of 3h plus 1 minus f of 0, which is 1, all over h. And of course we can't do direct substitution because we'll get a denominator of 0, but we can use the conjugate method. So let's go ahead and do the conjugate method. So this would turn into the square root of 3h plus 1 all over the square root of 3h plus 1 plus 1. We've multiplied this by the original. Now we can just use the conjugate method. So this will turn into the limit as h approaches 0. Now, if you FOIL the top, you should end up getting 3h plus 1 minus 1 all over h times the square root of 3h plus 1 plus 1. Well, the numerator is going to simplify. 1 minus 1 is 0. You end up getting the limit as h approaches 0 of 3h all over h times the square root of 3h plus 1 plus 1. Now notice you have an h that'll cancel out between the numerator and denominator. This now turns into the limit as h approaches 0 of 3 all over the square root of 3h plus 1, then plus a 1. We can now do direct substitution for h. Put in that 0. You would end up getting 3 all over the square root of 1 plus 1, which is 3 over 1 plus 1, which is 3 halves. So that means then that f prime of 0 is 3 halves. That would be the slope of the tangent line, or instantaneous rate of change, at the point 0, 1 for this function. Or the derivative at x equals 0 would be 3 halves. Now, of course, a big thing that these are used for, that derivatives are used for, a big application, are called particle movement problems. So we'll get into that. Let's see. A particle moves along a straight line with equation of motion S equals f of t. Find well, wait a minute. Where S is measured in meters and T in seconds. Find the velocity at t equals 2. All right. So particle movement and velocity problems are a huge application of derivatives. So we got a particle moves along a straight line with the equation of motion being s equals f of t. So s is the standard denotation of the position function. So s equals f of t, that's your position function. That's simply just the movement. And of course, the unit in this case for the movement is going to be meters, and the time is in t seconds. They want you to find the velocity at t equals 2, at the time being 2 seconds. In yesterday's lesson, we talked about how velocity was the instantaneous rate of change for the position function. Again, that makes sense. If I'm moving so many miles per hour or meters per second, that's technically a velocity. That's a change in position. That's all velocity is. Well, as it turns out, velocity is actually the derivative to the position function. So if we want to find the velocity function at a particular point, so in this case, we are given that f of t, the position function, is equal to t squared minus 6t minus 5. That is your position function. They want you to find the velocity at 2 seconds. Well, the velocity, we could call that v of t, velocity at time t, is the same thing as f prime of t, because velocity is the derivative of the position. So find, what they really want us to find is the velocity at 2 seconds, or find f prime of t. What's going to be helpful though is if we know the position at time equals 2. So first we need to find f of 2 itself. If we put in 2 into the original function, 2 squared is 4, minus 6 times 2, so that's minus 12 minus 5. At 2 seconds, so 4 minus 2 is negative 8, minus 5 is negative 13. So at 2 seconds, we're at negative 13 meters. So in other words, this would be at the point 2, negative 13. Now, what we need to do at this point, since we know the position itself, is going to be find the velocity at that time equals 2. So the velocity at time equals 2, which is the same thing as f prime of 2, is going to equal the limit as h approaches 0 of f of 2 plus h minus f of 2 all over h. Which now, wherever you see that t, put in 2 plus h. So this would turn into the limit as h approaches 0. Now put in your 2 plus h for t. This would end up being 2 plus h quantity squared minus 6 times 2 plus h minus 5, all that minus your f of 2, which is minus negative 13, all over h. Well, let's go ahead and simplify the numerator. This will turn into the limit as h approaches 0 of, we expand that 2 plus h to the second power, that'd be 4 plus 4h plus h squared. Now, minus 6 times 2, that's minus 12. Minus 6 times plus h, that's minus 6h. Minus 5 minus negative 13, that's plus 13. All that all over h. We can simplify the numerator a bit further. So 4 minus 12 is what? That's going to be negative 8. Minus 5 is negative 13. Plus 13 is 0. So all your constant terms are gone. Well, you'll just simply have now the limit as h approaches 0 of h squared. And then you have 4h minus 6h. Well, that's minus 2h all over h. Well, now we see we can factor out an h in the numerator. This would turn into the limit as h approaches 0 of the quantity of h times h minus 2 all over h. Well, of course, a common h cancels out. This would just turn into the limit as h approaches 0 of h minus 2, which we can do direct substitution for. You end up getting negative 2 for the value of the velocity at time equals 2 seconds, but that velocity, we need to put the unit, that would be negative 2 meters per second. So the velocity is going to end up being negative 2 meters per second when at the time t equals 2 seconds. That would be our velocity at 2 seconds is negative 2 meters per second. And I got just one more of these. Alright, it's going to be a different function. It's also a polynomial, but it's a higher degree, so... Alright, so once again, we're going to find the velocity of the particle at the time equals 2 seconds, but this time the equation of motion, the position equation itself, is f of t equals 2t to the third minus t plus 1. Well, of course, what we should do first is find the position at time equals 2 seconds. So if we put in f of 2 itself, that would be 2 times t to the third. Well, that's 2 to the third in this case is 8. Then just minus 2 plus 1. Well, 2 times 8 equals 16. Minus 2 plus 1. 16 minus 2 is 14 plus 1 is 15. So at the time t equals 2 seconds, we're at 15 meters. So this would be the coordinate to 15. When t equals 2 seconds, you're at 15 meters. Now, of course, to find the velocity at the time equals 2, that's the same thing as the derivative, which would be f prime of 2. That's going to be equal to the limit as h approaches 0 of f of 2 plus h minus f of 2 all over h. Well, now, wherever you see the t, you'll put in 2 plus h. So this is going to turn into the limit as h approaches 0 of 2 times 2 plus h to the third minus 2 plus h plus 1, and then minus f of 2, well, that's minus 15 all over h. On the side, I'm going to expand that 2 plus h to the third power. So let me just do that real quick. I'm going to use the binomial theorem real quick and expand this. And then I'll erase it because I'm going to put it into the function. Let me come down a bit so I don't run out of room. So 2 plus h quantity to the third, that's going to equal 2 to the third plus 3 times 2 squared times h to the first plus 3 times 2 to the first times h squared plus h to the third, which would simplify into 8 plus 12h plus 6h squared plus h cubed. So that wasn't so bad now that we've expanded that. So we now have the value of 2 plus h squared. So I'm going to rewrite this limit here then. So the limit as h approaches 0 of 2 times that 8 plus 12h plus 6h squared plus h cubed. All right, then minus the quantity of 2 plus h, that'd be minus 2 minus h, plus 1 minus 15, well, that'd be minus 14 all over h. Now we just distribute everything in the numerator. So 2 times 8, that's going to be the limit as h approaches 0 of 2 times 8, which is 16. 2 times 12h, that's plus 24h. And then you end up having 2 times 6h squared, that'd be plus 12h squared. And then 2 times h cubed, that's plus 2h cubed. And then you have minus 2 minus 14, that's minus 16 minus another h all over h. And now we can do one final simplification of the numerator. This would turn into the limit as h approaches 0. We only have one h cubed term, so that'd be of 2h cubed. Only one h squared, so that'd be plus 12h squared. And then let's see, we have 24h minus h, that'd be plus 23h. And then we have 16 minus 16 is 0, so the constant terms are gone. This would be all over h. Well, notice we could factor out a common h in the numerator, so this would turn into the limit as h approaches 0 of h times the quantity of 2h squared plus 12h plus 23 all over h. Now, of course, you have a common h in the numerator and denominator that cancel out. This would turn into the limit as h approaches 0 of simply 2h squared plus 12h plus 23, which we can do direct substitution for now. You put in 0 for your h's. You just get the value to be 23, but we need the unit, which is meters per second. So the velocity at time t equals 2 is going to be 23 meters per second. So that's how physics and particle movement problems from physics relates to calculus. Now, in the next lesson, we're going to talk about the derivative as a function. We're going to actually find the derivative of an entire function, which will enable you to find the derivative or the slope of the function at any given point on the curve, not just one point. So I hope everybody has a great day. Take care.